Okay, welcome back. We are going to do the rest of the packet called AP Practice Problems on Net Change. We did the first page together on a previous video. This was page 1. This was about gravel arriving and being processed at a gravel processing plant, and we got used to the AP exams style regarding asking these kinds of questions, and these are basically word problems. It is expected for this entire packet that you have a calculator with you, or at least at the time that these questions were written, you were expected when you solved them on the AP exam to have a TI graphing calculator. We have abandoned that now, but you still should have some kind of technology with you as you do these problems. So for that, I recommend using Desmos on a web browser, or GeoGebra, which is what I will use, or you could just use a calculator. Anyway, you have access to technology at all times, which means you shouldn't be spending basically any time doing any kind of algebra or differentiation or integration by hand. For that purpose, they've given us functions which are kind of ugly and disgusting and difficult to integrate by hand, or in this case, basically impossible. So we have to use technology. We also have been given sort of big numbers that may be what would really happen in a kind of scientific engineering application. So use your calculator freely. So therefore, you're being judged, maybe unfortunately for the magnet students, because you guys are kind of good at algebra, you're being judged not on your algebra skills, but on your ability to reason, think, understand, express yourself, and apply calculus principles. Okay, here we go. There's a lot to understand, and you're given exactly 15 minutes in a real testing situation to do these problems. That includes reading it, possibly reading it twice just to even figure out what is going on, taking some kind of note, and then getting started and figuring out all the answers to all the questions, and also, when applicable, justifying your work. So we're going to start right now. It's going to take us longer than 15 minutes because we're going to talk out what we're doing, and I'm going to also explain once again, using my super high-tech method, how to do this on GeoGebra. I'm going to show you how by turning the camera around, whatever. Okay, what's going on in this problem? Well, similar to the previous problem, they are testing you to see if you understand that the integral represents the net change, or specifically, if you know the rate at which some quantity is changing, then the integral of that rate is the net change. And so we are going to have something which is changing, and in this case the thing which is changing is water in some kind of a tank. And okay, so let's read. Water is pumped into a tank at a rate modeled by W of t equals 2000 e to the negative t squared over 20 liters per hour. Okay, so that's what it says right here. So we have this function, and I think it's important to keep in mind what this function is. I'm going to put it in a big red box. It is the rate at which water is being pumped into a tank. It's a rate function. It's not telling you how much water there is in the tank, but the rate at which the water is being pumped in. And the units are liters per hour, so that gives some kind of indication or helpful reminder that this is a rate function. Okay, that doesn't sound too hard, but water is also at the same time being removed from the tank. And at what rate is the water being removed? Well, here, and I think this is the first time we've done a problem like this, they're not giving you an explicit function for the rate at which water is being moved, because, okay, ideally we would like to use calculus to do science and stuff. And in science, you might not have access to a precise mathematical function which describes exactly the rate of change of some quantity. You might instead have to make do with some measurements. So notice that they were careful when discussing the rate at which water was being pumped into the tank. They were careful to mention that this is actually just a model of the rate at which the water was being pumped into the tank. So perhaps there is some kind of fancy, advanced statistical methods which were used to produce this function as being, the function of best fit for some kind of data, and now we've decided to adopt that as the model. But at an earlier sort of stage in the analysis, you might not even have a model at all, or at least you might not have an explicit formula for the model. You might just have some discrete data points. So this is maybe more like like a real kind of a scientific application. And okay, so this is the rate at which water is being removed from the tank. We're calling this function r. This is just me reproducing the original chart from the top of the paper. This function we're calling r, and r is the rate at which water is being removed. So the rate at which water is being pumped in, the rate at which water is being moved. And we know this function only for select values. So you can imagine the units of time are hours. So at sort of time 0, at the beginning of the day, we took a quick measurement of the rate at which water was being removed. At time 1 hour, we took a quick measurement of the rate at which water was being removed, and et cetera, et cetera. Note that these aren't even equal with subintervals. So we didn't even measure once per hour. We measured it at hour 0, 1, 3, 6, 8, so who knows why we did that. Okay, and based on this only, this is the only thing we know about this function r. Except it's decreasing, and differentiable seems to be a kind of a crazy thing to say, but okay, assuming that the water is being removed according to the basic laws of physics, then okay, any simple function measuring continuous motion is going to be basically a continuous function in this sort of macroscopic world. Okay, and it's decreasing, so that's kind of important that we know that we happen to know for some kind of reason that this function is decreasing. Notice that this is the rate at which water is being removed. That rate is decreasing. So we're removing the water sort of quickly, and then later on we're removing the water more slowly. And there was some tiny, I don't want to call it a typo, it's just some sort of smudge on the paper or something, which made it look maybe like there was a little negative there, but of course no, there is not, because this is a decreasing function. Okay. The last piece of information, very important, is that at time 0 there are 5,000 liters of water in the tank. Okay, and now finally we begin the problem. Alright, let's go. The very first thing it says to do is to estimate r prime of 2. Estimate r prime of 2. And this might strike you as vague, and you might have just absolutely no idea what to do here. So for the moment, just forget about the fact that r itself is a rate function, and just take r as being just some function, man. I want to know what the derivative at 2 is. Well, I have no idea what the derivative at 2 is, but the only thing I do know about this function is the value at time 1 and the value at time 3. And so the derivative of the function r at 2 is going to be roughly equal to the average rate of change of this function on the interval 1, 3. And so basically we just say, okay, look, the change in r on the interval 1, 3 over the change in time on the interval 1, 3 is going to be approximately equal to the derivative. And if you want some kind of picture of this, well, here's 1. Well, I'll just draw a generic function. Here's 2. Here's 3. If I have some kind of function, and I don't know anything about it except its value at 1 and 3, and I know it's decreasing, well then, the derivative at 2 is the slope of the tangent line, so the slope of the tangent line is not going to be too far off from just the slope of the secant line on that interval. Anyway, it's the only thing we can do, because we don't know what's going on at 2 exactly. Okay, and so now you're supposed to just do this computation. In other words, r of 3 minus r of 1 over 3 minus 1. Okay, and what is this? Well, r of 3 is 950, so that's 950 minus 1190 over 2, and when you do that, you get negative 120. Notice how in this problem, unlike the first page, they don't ask you to explain in words what this derivative is, but they do ask you to give the units. So if you give the units, it shows that you have some kind of idea what's going on. And what are the units? Well, R is in liters per hour, and so the derivative of something which is measuring the liters per hour is going to be liters per hour per hour. After all, the numerator here is going to have units liters per hour, and we're dividing by a time. So this is going to be negative 120 liters per hour, and most people would just say that this is negative 120 liters per hour squared. Okay, so that's the answer to this problem. That's all you have to write. Maybe it's worth just quickly talking about, what is this anyway? If R is the rate at which water is being removed, then R prime of 2 sort of says the rate at which that is changing. In other words, if I were to put this into a sentence, I would say that at time 2, the rate at which water is being removed is decreasing at a rate of 120 liters per hour per hour. That's what the negative derivative of R tells me. It tells me that R is decreasing, and specifically it tells me the rate at which R is decreasing. Okay, moving on to part B. What's going on in part B? Here we go. What do they want? And I just used my calculator for these numbers, but okay, I almost didn't need to because they were not so big, but you certainly could and should maybe. Part B. Use a left Riemann sum with the 4 subintervals indicated by the table to estimate the total amount of water removed from the tank during the 8 hours. Is this an overestimate or an underestimate of the total amount of water removed? Give a reason for your answer, which is a little bit less than justify, but still it sort of gives some kind of explanation. Okay, almost no one does this, but it actually only takes like 1 minute, and I find that my ability to think about what's going on is much improved if I draw a little tiny picture. And the picture doesn't have to be accurate or anything. So here's 1, 3, 6, and 8. Okay, and all I'm going to, maybe I'll draw a better picture. So yeah, 1, 3, 6, and 8. And where am I at time 0? I'm up here at 1340. Where am I at time 1? At 1190. Where am I at time 3? 950. Here's what I mean by not that accurate. Where am I at time 6? 740. And that's 6 and that's 8. And where am I at time 8? 700. So that's just going to be a tiny bit less. Okay, 700. And here's 8. Okay, great. So the first thing that they want is estimate the total amount of water removed from the tank. Well, if this is the rate at which water is being removed, then the fundamental theorem of calculus says that the integral of the rate of change of some quantity is the change in that quantity. Or you might say that this is not the fundamental theorem of calculus, but just some basic principle of what integration is. In other words, if I take the integral from 0 to 8 of r of t dt, then I'm going to get the total amount of water removed. So that's just what to do. The only problem is, if I was given an explicit function for r, then I would simply integrate it, and that would be that. But here I don't have an explicit function, I only have discrete data. So I have to estimate what this integral is. And so here we are sort of testing if you understand that an integral is really just a sum. And if we have only discrete values, then we have to just find the area under these discrete values, so to speak. And specifically, they just tell you, use a left Riemann sum. In other words, they're telling you to find this sum, in other words, to estimate this integral using a left endpoint approximation. And so here you're given 4 subintervals, 5 pieces of data, which leads to 4 subintervals, and on each subinterval to use the left endpoint of the subinterval as the estimate for the value of the function. So here's why I think the picture's kind of nice, because it sort of reminds you that the these intervals are all of unequal widths, so there's some sort of thinking that has to go on here. And so what are we going to do? We have to take the areas of the rectangles one at a time. This is 1340 is the height of this rectangle, but the width is 1. And here the height is 1190, but the width is 2. And here the height is 950, but the width is 3. And here the height is 740, but the width is 2. So times 2. And when you multiply all those together on your calculator, you never use this 700 value at all because it's a left endpoint approximation. When you do all that on your calculator, you end up with 8050. So the answer is to one of the answers to this section is 8,050 liters of water have been removed over the time interval 0 to 8. And now the question is this an overestimate or an underestimate? And okay, they don't expect you to say a lot here, but they do expect you to just know some things, which are also just kind of common sense if you look at what's going on, which is that okay, I don't know what this R function is, but I do know it's decreasing. And here, the fact that they tell you it's decreasing is very relevant because it means that you don't have to imagine that maybe the function's sort of crazy or something. We just know that this function R is decreasing, and now we just simply cite the theorem that for a decreasing function, LRAM is an overestimate. So that's all you have to say. So something like since R is decreasing, LRAM will be an overestimate. And okay, drawing the picture, it's certainly not necessary to do the problem, but it kind of reminds you of all the things of what you're actually doing, and now it's sort of obvious that this is going to be an overestimate. Okay. Cool. I think that's it. Good. That was part B. 2 to go. C is, I think, quite sort of short and simple. Part C says, use your answer from part B, in other words, it's 8050, to find an estimate of the total amount of water in the tank to the nearest liter at the end of the 8 hours. Okay. So, so here's part C. So the question is just, how much water is going to be at the tank at the end of the day? Well, I think this is actually a pretty easy question because, well, you just reason it out, right? There's 50,000 liters in the tank at the beginning of the day. And now, how much water has been pumped into the tank? Well, if W is the rate at which water is being pumped into the tank, then the integral from 0 to 8 of W will give the total amount of water which has been pumped into the tank during those 8 hours. And if we then subtract from this the rate at which the integral from 0 to 8 of R, R being the rate at which the water was removed, then this is the total amount of water pumped in, this is the total amount removed, this is how much I started with at the beginning. So you just type all those numbers into your calculator. For this, we use the 8050 from the previous step, and for this, you just type into your device integral from 0 to 8 of this W function. Okay, and I got an answer, and my answer was, I think, they say round to the nearest liter. So you get I got 49786 liters as my answer. Okay, good. This leaves now part D, which I think is quite hard. Well, this is not really quite hard. It's a little bit hard. It's a very theoretical question. What they're saying is there a time t when the rate at which water is being pumped into the tank is the same as the rate at which water is removed from the tank? Explain why or why not. Okay, so you have this function which expresses the rate at which water is being removed, and this is the rate at which water is being pumped in, and the question is, are those two curves ever equal to each other? Alright, we'll go way back to a long time, like February or something, And we had this whole conversation about showing that sort of two functions are equal. And what we said was, yeah, there's this sort of common sense kind of little theorem that says, dude, if I have some function that starts high and ends low, so call that f, and I have some different function g, which starts low and ends high, then like, just come on, those two functions must intersect. And while that's sort of extremely plausible that that's true, and you might get some credit for just sort of rambling that fact, actually this is an application of the intermediate value theorem. And so you perform this kind of trick, I guess I will call it, it's a trick we've seen before, though, where you create a new function which is the difference of these two functions. So, let I define a new function f be w of t minus r of t. In other words, let this f function be the difference in the rates, or the difference in the values of these two functions. We don't even have to talk really right now about them being rates, because all that really matters, they're really just asking, is w ever equal to r? And I guess the answer is yes, because look, when I plug 0 in for t, I get e to the 0 is 1. So this w function starts very high at 2000. But I bet by the time we get to 8, I bet that it's going to be much, much smaller than 700. So I think these do cross. Okay, but I'm going to show it on the calculator in a minute. So let f be this function. Now here they want you to really like kind of show off your understanding of this. What I would like to do is to apply the intermediate value theorem, but first you need to say a couple things. So since r is differentiable, that's what they told us in the problem, then we know that r is continuous. That's important because, okay, every differentiable function is also continuous, or rather if a function is not continuous, it's not differentiable. This is a theorem we proved. So since w is a continuous function, and I'll just write also w is continuous, because it just is, it's an exponential function. So if w is continuous and r is continuous, then f is continuous on the interval 0, 8. And now, what we need to do is to find some values for which this works. And I'm going to sort of tell you right now that I just plugged in 0 for f of 0. And, well, I already sort of told you, right? If you plug in 0, you can just see, even without a calculator, that w is going to be, is going to be 2000. So the w function starts at 2000. And the r function starts at 1340, so f of 0 is just 660. But f of 8, so now we just check to see the values at the end of the day, and okay, f of w of 8 I can't do in my head, of course, but this is 700, and we'll do this in a second. But the answer is that I get negative 618. 0.476. And so, squeezing this in, conclusion, so apply the intermediate value theorem to f on the interval 0, 8. And what does the intermediate value theorem say? It says, we say something like, since since f of 8 is a negative number, and 0 is the y value in between f of 8 and f of 0, then what we know is there exists a c on the interval 0, 8 such that f of c is 0. But if f of c is 0, then that really means, based on our definition of f of c, that w of c minus r of c is 0. So w of c equals r of c. And thus, we have proven that there is a place where the w function and the r function are equal by applying the intermediate value theorem to the difference of those two functions. Really all we're doing is we're using sort of fancy calculus language to state the obvious, which is if one function starts high and ends low and the other function starts low and ends high, then they have to meet somewhere. And it's the intermediate value theorem that enables us to conclude that they do meet. It's the intermediate value theorem applied to the difference of those two functions. And they really do want you to go through all this. We did this. This was the mountain problem once upon a time when we were back at Blair. Okay, I think that's it. Let me show you how to do all these things on GeoGebra and also how I maybe sort of came up with these numbers in the first place. So super high-tech move coming where, oh my god, where we do this and this and this and yeah. Okay, sure. I'll try not to get in the way. So what's the, just to kind of review, I don't know, maybe this is not necessary, but I go to geogebra.org, I go to over here, I click on graphing calculator, I go here, and I type the w function. This is maybe the very first thing you can do at the very beginning of the problem, just so you can get a look at the function, see what's going on. It's 2000 e to the negative t squared divided by 2000. And there it is, brilliantly sort of formatted. And everything is good. Okay, I want to look at this only on the interval 0, 8, so I'm going to go over here. And I also don't see the function. I'm going to just, I guess it's going to be huge. It's going to be like 2000, right? So there it is. Okay, well anyway, this window's all messed up. So I'll change my X-min. Well, I only want to go from 0 to 8, first of all. So enter, go, and this is 8. And here is, I guess just 0 is fine. And here, my y-min I need to be like 2000. And I guess it auto does everything else. That did not work. Or did it? Something went wrong. Negative, because it's over 20, not 2000. That will explain it. Okay, boom. There we go. Okay, so now we get a beautiful function showing that, yeah, we do start up at 2000, and by the time we're done, it's close to getting down to 0 actually. So that's sort of interesting. Okay, so great. What's the one other thing that I did kind of off screen is I took the integral from 0 to 8, and so in fact what I actually did was I did 50,000 plus, this is part C now, plus the integral from 0 to 8, so integral, boom, this guy, the function I want to integrate is how does it do that? Is w and okay, still haven't totally mastered this, but I want to do numerical integer w from 0 to 8, and then I want to, this is bothering me a little bit, there we go, and then I want to subtract the answer that we got from part B, which is 8050. Boom, boom. Alright, and there's the answer. So I think easier to error check than on the Texas Instrument calculator. Anyway, there was our answer to part C. What about part D? Well, I think here we can just kind of now, once you're just sort of looking at this function and also looking at your R values, Well, you can just see clearly, right, that the r function starts up here at around 1340, and at the end is at about 700. So it's just sort of obvious that this r function is going to cross. If you wanted to be super fancy, I don't think this is a good use of time, but you could even just plot a bunch of points. Like there's a point, 0, 13, 40. I guess I'll just do this for a second. 1, comma 1190, 3, 950. So boom, 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 and 6. Oops. 6, 740. Bum, bum, bum. And finally 8, 700. 8, 700. So what am I doing now? Well, these 5 blue points are, if I were to connect them, basically the R curve. So I think it's very clear now that these two functions, this W function and this R function, do kind of cross each other. And when it comes to applying so that you should be thinking that I need to apply the intermediate value theorem. And so the only other thing I did using the technology was to just get f of 8. And f of 8 we said was W of 8 minus R of 8. And so I just can remember, I could just type, W of 8 at any time. Minus, and R of 8 is 700. And when I do that, I do get that negative 600, which is clear that it will be negative because the R function is bigger than the W function here. Okay, but math, I don't think we need to go back to the other board. I think the justifications were all there. Good, I'm sure that was extremely long. Goodbye.